in working order. Well, good morning again. Yes, gentlemen, in fact, we don't have any ladies present. Once again, welcome. Thanks very much for being here quite early in the morning. Before I briefly introduce Bill's second talk, the programme for today, Bill will speak first, giving the second talk, and then Colin will be giving his first talk on cohomology theory as foundations. Sorry, have I got the right title? Sorry.
In categorical foundations.
In categorical foundations, yeah, okay. Yes, cohomology in categories as the foundation, which will be the second talk of the morning. And then, while Bill or Colin are talking, I will slip across the road and see if there is any way that we can go for lunch to the university cafeteria in the campus of University Nancy 2, which is across the road, which would save us a lot of time. And all the dispersing for lunch yesterday was not a good idea. We lost rather a lot of time. However, if, as I suspect, that cafeteria is closed already for the vacation, then I would suggest that we go down, since the cafe that the other cafe I was relying on is also closed, as we found out yesterday. I would suggest that we go down to the corner of the Avenue de l'Armée Platon and get sandwiches from the little sandwich bar on the corner, rather than having to sit down at lunch, just so we can keep on schedule. And then we'll come back here in the afternoon, starting at 2:30, well, depending on what time we have break for lunch, but aiming to start at 2:30, for the contributing talks, and we will have 3 contributing talks, Andrei, Panagis, and then we hope a talk delivered by WebEx, Skype connection, from California, from John Stachel. So that's the programme for today. Without more ado, may I again introduce Bill, who is going to give his second talk, which in fact is transposed in the programme. His first talk was in fact on the subject of space as an object in the category of spaces and its various determinations. The title of his second talk is The Dialectic of Continuous and Discrete in the History of the Struggle for a Usable Guide to Mathematical Thought. Bill.
Thank you. Well, the reason I permitted it, you see, the title is from space to sets, and so more or less. I'm a bit sorry because this morning I was going over my notes, trying to decide which set of notes to use to follow, and I find, well, as you might expect, there's some points I really want to make in one that isn't in the other, and in one. So what I should have done was to sort of merge the two together in one document, but I hadn't really realized that was necessary. One set of notes is from a talk in Firenze a year ago, and the other one is from a talk in Bristol, April 1st, 2009, 2 years ago. So I'll try my best to make a single narrative out of this. Okay. The philosophy of mathematics in the tradition of Grassmann and of a few others seeks to provide a guide to the development of mathematical thinking based on discovering and making explicit the fundamental trends in the science. Nodal points in the development of the philosophy of mathematics occur when most of the main threads so far discovered can be expressed in a single, finitely presented algebra. That's what the theory of the category of categories aims to be. Single, finitely presented algebra that permits the expression of most of the so far discovered threads in the development of mathematical thinking. Now, difficulties in approaching, of course, Grassmann, I say Grassmann and a few others because most people don't define foundations in those kind of terms. But anyway, so the difficulties in approaching the above program have resulted from the accumulated culture of the so-called set theory, so that my discussion needs to begin with some efforts toward sweeping away those cobwebs. I say so-called because actually the meanings, there are at least 7 entirely different meanings of the word set, which are often confused in polemics. Moreover, again, another reason for the so-called. I learned from Tarski and Scott and so forth to always think of theories in terms of models. So if we think about a model of set theory, it does not consist of sets, does not consist of collections. The points in the universe of the model. Of course, these points determine sets because of a given binary relation, which is any binary relation at all would give rise to a method of parameterizing some of the actual subsets or subcollections of this model by elements of the model, any binary relation. So the epsilon relation is not special in that regard, and it really from the beginning has to do with parameterizing certain families of sets rather than actually consisting in some direct way of sets. So I think these very general simple points need to be kept in mind. Now what is usually called set theory is really the theory of the Frege, Peano, Zermelo, von Neumann hierarchy, not the theory of Cantorian sets. And, as many people have remarked, although I get some of the blame for it, the theory of that hierarchy has not fulfilled the above-mentioned philosophical goal of assisting the development of mathematical thought. It's assisted a lot in the development of its own pursuit of infinity, but not really mathematical thought so much in other fields, except near the beginning, countable additivity and all that got clarified with help of, again, any set theory would do, for example, the hierarchy theory for that. But after that, now, so I think the first thing is just to distinguish between sets and subsets. In elementary study of mathematics, like say advanced calculus or various subjects like that, what we talk about or called sets are really subsets. Subsets of the plane, subsets of three space, and so forth, and can be described by coordinatization and by properties of triples or pairs and so forth. But advanced calculus, and indeed no mathematical subject, provides any basis for the idea that R3 and R2 are themselves, in some intrinsic way, subsets of something else. If they were, as Frege asserted, well, Frege derived this from the philosophical principle that the only concepts in mathematics are properties. And taking seriously this universe of discourse concept, which is really necessary to make logic work at all, and mean anything at all. Frege, properties, meaning properties carved out of the universe of, quote, everything, unquote. But interesting statements, in fact, require some structure of the universe, or you have no interesting statements to make. Hence no properties, hence no concepts, according to this. So it was Peano's interpretation in terms of epsilon and singleton, which actually Frege celebrated. He wrote a letter to Peano saying, "This is great, now finally we have this." This facilitated the perpetuation of the claim that the development of mathematical thinking is limited to passage from one statement to another about this big universe. In practice, however, practice of mathematics, however, universes such as R3 and R2 have their subsets, but among the transformations between the two universes, there is typically no preferred transformation. If it's in this one. I actually tried to write out a development of Frege beyond set theory, starting from that conception of what it's all about. But I guess I don't have it here. Maybe I have time to mention it. So basically, this passage from one statement to another, I have sometimes, for reference, called subjective logic. And the point is that there's also objective logic, the development of concepts, one from the other. And this, again, for rough division, I call objective logic. And of course, there was very little in the way of formalized objective logic until, as you know, categories, which is a big step in that direction. So, in other words, nearly a century ago, set theory, quote unquote, on one hand, and mathematics on the other hand, essentially parted ways. Mathematicians like Emmy Noether protested that the sets used in mathematics are quite unlike the hierarchy, citing, in fact, Cantor and Dedekind as having a specifically distinct vision from that of the hierarchy. Actually, Max Zorn, whom I was privileged to share an office corridor with when I was at Indiana University, he sent me a quotation from Hilbert that he thought strongly supported a similar view of that of Noether, Cantor, Dedekind, as opposed to the usual doctrine. Zermelo contributed to this split by endorsing Frege in opposition to Cantor, even as he was editing Cantor's works, and in particular by failing to appreciate that the Cantorian abstraction process begins with distinctly cohesive mengen, and he condemned that process as bringing no progress. For Neumann, so far as his philosophical basis, he simply says that he followed Zermelo. Maybe so that he knows some other philosophical principle for Neumann, other than undertake preventive nuclear war and all this other things. But, so there's a quotation from Zermelo referring to this attempt to base the theory of the cardinals on cohesive sets. Der Versuch war kein glücklicher und wir sind keinen Schritt weitergekommen. That's on page 351 of Cantor's selected works, because Zermelo liked to insert his own footnotes to Cantor's papers. However, obviously, the Cardinalzahlen of cohesive spaces can be isomorphic, even though the spaces themselves are not. Now a well-known Cantorian phenomenon that in some sense the cohesion involves more structure than the Cardinalzahlen, which is by the Cardinalzahlen, by the way, is Cantor's name for what we call abstract sets. It's not a name for the equivalence classes, although of course he understood about these equivalence classes, but he used the term Cardinalzahlen as nearly as I can make out for these arithmoi or abstract sets, whatever they're called. It's just a hair less abstract than Cardinalzahlen in the current usage, which is representatives for the isomorphism class or some such thing. One of the most destructive effects of this split was the belief that the foundations of mathematics is intrinsically of a different character from ordinary mathematics. Category theory, again, provided an instrument to begin to refute such a belief. So that, as our theme is geometry and set theory, have many things in common, direct relationships. So, again, to belabor the same point, properties and statements occur constantly in mathematics, but that by itself leaves the question, properties of what, statements about what? Mathematical practice has inherited from Cantor and Dedekind the fundamental guide that the properties and statements concern structures of a certain shape and a certain, in general, cohesive background, such as Lie groups. That is...
I hate to interrupt. Would you prefer to speak sitting?
Would that be better?
Well, it would mean that you weren't having to make squeaky noises.
I take my shoes off.
No, I just suspect it's going to be rather distracting when we listen to the...
No, I guess my role here is to pose as a philosopher anyway.
If you prefer to take your shoes off, that's fine.
Can you make it a little more precise what you mean by cohesive? Or is it a word that
Read my
Gonzo
paper.
would use?
Read my paper, Axiomatic Cohesion and Attack Online Journal.
But that's a word of yours, I mean, not of contract, for instance.
Well, okay. In that paper that I cited, as well as many other things, I'm trying to explain the historic struggle between continuous and discrete.
Mm-hmm.
But the problem is that for over 100 years, continuous had a very particular determination in mathematics. So you can essentially take cohesive to mean continuous, but in a more philosophical sense, not limited to, open sets and all that. Right. So that's the first approximation. Yesterday, Jean-Pierre used another word. I realized it's something similar, actually. Connectivity. A cohesive space, whatever it is, it has something called connectivity. And you can sort of, reduce the qualitative aspect of cohesion to connectivity, to form as opposed to substance, etc. So form and substance, by the way, have formal definitions. Okay, so structures of a certain shape in a certain background, I say certain. So, by the way, there's an interesting dialectic here, which was pointed out, specifically, but not developed at all, by Murdijk and Reyes in their book on the infinity toposes. Namely, the same structure can be described as, take the example of Lie groups as very important. You can think that Lie groups are structures of a very simple, relatively simple shape, namely the shape of group, but in an already very cohesive background, namely the C infinity or AC infinity topos. On the other hand, you can take the view that the cohesiveness itself is a kind of structure interpreted into abstract sets, in which case the theory of Lie groups is much more complicated as a theory, because it contains all the stuff about the cohesion or the smoothness or whatever as part of the specification of the shape of the structure, yet the background is the things that are as structureless as possible. So the fact that in this representation of the idea is if we take C, a concept, a mathematical object, realized as a category, we can represent it often as a full subcategory of the functor category, B to the power A. B is a background and A is the shape of structures. But there are many such relationships. That's why, in particular, I refute the strong structuralist claim that mathematical objects are structures, because in fact they are just objects in categories, and they have many representations of that structure. But in particular, these different representations have this kind of idea, more into the shape, less into the background, or the other way around. So a concept can be represented as a structure with a property. Serious properties, as opposed to mere properties of the shape itself, have to do with cutting down the full functor category B to the A, as defined by Grothendieck, down back to the full subcategory C. These properties maybe go well beyond what can be put into the shape itself. But anyway, with category theory, we can clearly distinguish between two things, namely, is represented as or is. The distinction being necessary because a given concept may have several representations, just as a vector has many representations as a tuple of numbers. So with his Kardinalzahlen, consisting of lauter Einsen, beautiful phrase. Actually, I started on this whole thing because Mayo pointed out this phrase, lauter Einsen, in this book, Cantor's Collected Works by Zanello, saying that, well, it had something similar to what I've been saying in my lectures. So this is, leads to quite a journey to Cantor's writings, actually. Anyway, he revived, I say revived because of this Lawvere's idea that, well, really these are the ancient arithmoi, but specifically extended to infinite sets. So the idea of a cohesive background can be abstracted to one of ideal non-cohesion. So this ideal non-cohesion, so I'll come back to. But making this abstraction not only made possible the measuring of the size of infinite sets, by the way, an idea which Cantor explicitly said he got from the algebraic geometer Steiner. No set theorist knows that, even if they read this book. It's anti-consciously sets in when they... But this abstraction also supported dialectically the analysis of cohesion itself as a special kind of structure on a structuralist set. And when mathematicians in general speak of underlying sets, or when they describe a result as ensembliste, so on, they mean these abstract structuralist sets. They do not mean elements of the von Neumann hierarchy, unless they've been thoroughly brainwashed. Most practicing mathematicians, when they say that. Now, it's also striking that when Cantor noticed that you could do this, he became very excited. You can see from reading his description of it. This is great, you see. He hypothesized early on that for these cohesion-free infinite sets, there would be no isomorphism types between x and 2 to the x. In other words, the motivation for the continuum hypothesis is not just some conjecture about possibilities. It comes from the partially realized conception of what these really structuralist sets would be like. And again, I underline again and again that the very basis of Cantor's theory, which is that, and of the GCH in particular, completely ignored by all practicing set theorists. One thing that I'm pleading for here really is a more serious analysis of this idea of variation cohesion versus structuralistness, and particular emphasizing the structuralistness. Now, from later work by Gödel, thinking of the incompleteness theorem, we conclude that it will not be possible to completely express this idea of freedom from cohesion. Well, can't completely express anything, not true. That's no particular image. But on the other hand, we can certainly make very strong statements that partially express this discreteness. The explicit introduction of the axiom of choice was, in particular, a recognition that the abstract sets are something qualitatively different from those that have anything more than just a trace of cohesion, because then the sections don't always exist for surjections, because a trace of cohesion prevents arbitrary sections. Now, although the idea of freedom from cohesion is not itself iterative in nature, we can apply this Cantorian abstraction process to Gödel's, von Neumann's Gödel's constructible hierarchy, L, to obtain a partial model of it, where it means freedom from cohesion. That is, a category of abstract sets in which Cantor's hypothesis is true. Now, this was carried out by Gödel, as we know, a long time ago. But notice, I didn't remark, you see, it's not only true that mathematical statements of interest have no real dependence on the hierarchy. It's even true that most statements of a recognizably set-theoretic character do not. So the axiom of choice, the continuum hypothesis, measurable cardinals, these typically set theoretic things do arise occasionally in mathematical practice, but in particular, they do not depend on the hierarchy at all. Now here's the way we can formalize this idea is, well, take anything that can in any reasonable way at all be called set theory. So you will at least have a definition of ordered pairs and functions and maps and so on. So from any model of set theory, you can extract by definite, well, I think of a functory. So you go from the category of models into the category of categories. Then we can extract a model of the theory of category sets from any model of set theory in that way. So the point is, all these interesting properties, both mathematical and most of the metamathematical ones, factor through this process. They only depend on the category of sets that's extracted from the model of sets. And that's true, of course, of Cantor's hypothesis in particular. So, the idea behind this is that, well, somehow one way to achieve this abstractness, this freedom from cohesion and variation, there are many ways to express the rough idea. One way of obtaining it is to perform Cantor's constructible hierarchy and then extract the category of sets from that. Well, obviously this is a roundabout way, since the conclusion has nothing to do with iteration. So the problem is to really find additional axioms for the category of abstract sets which force the continuum hypothesis and so forth, because, not for just some formal reason, but because they express this idea of freedom from cohesion and variation. By the way, yes, we used to talk about variation, and indeed to some extent the cohesion can be expressed through a kind of variation. On the other hand, later I realized that, well, really there are sort of two features. For example, in any topos, or any topos defined to another one, there's an aspect of additional variation, there's an aspect of additional cohesion. Some are really overwhelmingly one, some are overwhelmingly the other, there's all kinds of interaction, and so forth. So when I say cohesion, you could take cohesion and variation. And in fact, there's an interesting point here that most, but not all, of the so-called independence results in set theory really proceed by this strange method, by introducing additional variation and then sort of killing it as far as we can see. In other words, finitely expressible properties of something that's variable, and then sort of almost made constant but not really, can reflect some of the features that you attribute to, or refute some of the features that you attribute to this abstractness. But just by going through this, and another point is that there is, for example, the Mansfield's completeness theorem for infinitary logic, or Barr's Delineus proofs that toposes have enough points of one kind or another, which in principle, or in among other things, they show that the mere subjective logic of the topos can be faithfully interpreted in one where the point is variation, mere variation, not the cohesion as such. But this is only the subjective logic part, not the geometry part. It needs to be also kept in mind. Now, the consistency of the theory implies the existence of a model. It is then possible to strengthen the theory by joining some of its classes and describing them in a first-order way. Now, here by a class, we mean objectively a subfunctor of the underlying functor of the category of models. Something that's there in every, but it's a subfunctor, it's not an element. Now, this strengthening was applied by Craig and Watt to show that any recursively axiomatizable theory is one that has a finitely axiomatizable conservative extension. This was a general formulation of the principle used by Bernays and Gödel to arrive at their well-known finitely axiomatizable theory of the hierarchy. Now, this principle of strengthening a consistent theory would permit even a Cartesian closed system of natural classes. But Bernays and Gödel made a truncation of that, allowing only one step, even though the relative consistency would not be harmed if such closure were allowed. That obviously depends on the kind of topos in which you interpret your models. But now, MacLean, who we should remember was a student of Bernays, referred in 1945 to this truncated theory as a possible foundation for category theory. And that very unfortunate tradition of illegitimacy of functor categories ensued. So that many category theorists reflexively say, well, this is an illegitimate category because it merely formed a functor category of two actual categories. This was because what MacLean laid down was the idea of locally small categories and so on. But again, small was defined only in terms of the Bernays' principle. Come back to it in a moment. However, very interesting, this is pointed out by Janowski, actually, that in the 1963 correspondence between Gödel and Bernays, they were reacting to the needs of category theory as expressed probably in I suppose they were reacting to his introduction of locally small categories in Warsaw in 1950. In any case, they had heard that there was this thing called category theory and these problems, possible problems, so they were corresponding to that. So in spite of the fact that they were the ones who laid down this notion of legitimacy, they had no ambitions against saying, well, of course, obviously what we need is finitely many types of both. The law enforcers take it more seriously than so now this above conception of classes, namely the subfunctors of category models, applies to any theory, not necessarily just to a theory of sets or a theory of categories. In the case of the theory of categories, the classes were called by MacLean and the metacategories, just to avoid confusion with the elements of the universal discourse, which may be called actually existing categories for emphasis. Now, the possibility of representation of certain metacategories by actual categories is naturally interpreted in the sense, not of equality or membership and so on, but of categorical equivalence. So that, for example, the metacategory of finite discrete categories is represented by the category of finite sets, meaning any up to equivalence chosen category access finite sets. And it's hopeless to try to make any distinction between them, except, of course, they're skeletal, that's kind of distinguished, but who can use that anyway? So it is absolutely fundamental to me and to Grothendieck and the Tohoku that the functor category of any two actual categories is actual to the same extent. This is, Grothendieck laid this down as fundamental. I independently believe it's fundamental. I agree with Grothendieck on this. In other words, the garden variety of illegitimacies is simply not arrived, because you can form these functor categories and they're still actual. Of course, since local smallness is a specific kind of enrichment, namely enrichment in the category of small sets, I'll come back to what that is. The functor category of two locally small categories need not be locally small. That's an objective property, not a matter of enrichment or not. And there's a clear analogy. The functor category of two locally finite categories need not be locally finite. This should be something that's perfectly evident and acceptable. Local smallness is a particular form of enrichment, and even though enrichment is not required for the formulation of certain fundamental notions, such as adjointness, I pointed this out in my thesis. I mean, most formulations of adjointness presuppose enrichment of the two categories involved in one way or the other, but there are at least two ways. One in my thesis in terms of the so-called common categories, the other in terms of the two-dimensional structure, which don't involve the assumption that the categories are enriched in small sets. So in some sense, the crucial issue of large categories, why are large, becomes that of defining or hypothesizing a notion of small set, and assuming that notion is representable by an actual category, as opposed to a small set, well, it is itself some kind of meta-category, but it should be representable by an actual category. By going only slightly beyond the relatively consistent theories thus far alluded to, but not at all beyond the size considerations commonly considered by set theorists, we can propose an outright definition of small sets. So, let's review, again, from my paper on the category of categories. It's interesting that the category of categories appears in Rother's homotopy theory, for example, as a kind of geometrical category. Already in Heidelberg-Steenrod's book on algebraic topology, they say that we can think of these commutative triangles as being simple series and stuff like this. But somehow the category of categories has a geometric character. So again, hopefully in keeping with the theme, the interesting thing is that the standard method that I discussed before, representing sort of arbitrary geometrical categories in terms of figures and incidence relations, I actually discovered in connection with the category of categories. And, well, Rosie elaborated about roughly the same time. So the idea was to represent a concept C according to the notion of structure and property by finding a background B and a shape or theory A, and define somehow a functor from C to the functor category, B to the A. We strive to make this functor full and faithful, in which case C can be carved out by properties of some sort from the A-shaped structures. For later use, we can distinguish between A-shaped algebraic structures and A-op-shaped spatial structures, although of course A is an arbitrary category, the distinction like here, but in a given context. We usually have those A-shaped structures, which are of an algebraic character, and A-op-shaped structures, which are more precisely these figures of incidence relations and so on. Now, the experience, as I said already before, experience shows that the same concept C has typically several such representations in terms of structure, shape, background, and properties of structure. This method of analysis has a much sharper internalizable form. This is not usually pointed out, but as I say, it's already a category. But applying it to geometry is the aim. The internalizable form, motivated by geometry, will provide us with a guide to axiomatizing the whole category of categories. Because if C is a Cartesian closed category, and it has the Hurewicz exponential adjoint product, and this is a fundamental aspect of mathematics, since Bernoulli's calculus of variations, I claim, and so on. But if C is Cartesian closed, and if A is any subcategory, we can define a subcategory B by the condition B equals B to the power A for all A and A. In other words, those objects B, such that there are no figures of shape A in it except constant single points. So all A-shaped figures in little b reduced to points, and I'm using capital B as a category of all such little b. So again, this equation, B equals B to the A, like any binary relation, determines a Galois connection and the resulting Galois connection in closed classes of objects for these Galois connections should be considered as connected and discrete. Each of these A's looks connected as far as the B's can see, and each of the A's seems to be, each of the B's seems to be discrete insofar as the A's can see, because the A's can't get any motion going inside the B. Galois closure of this relation, which makes sense in any Cartesian closed category.
So the idea of D would be something like small sets?
No, discrete.
Discrete.
But yeah, we're coming to that, yeah. Trying to make them small to an extent. So I say, well, essentially always B will obviously again be Cartesian closed and co-reflected just by basic morally. I mean, the minimal assumptions of category theory will guarantee that there is a co-reflection, so that every object, every space, call the objects of the categories these spaces. Every space has a maximal discrete subspace, which could be called, the set of points of the space. Of course, the situation is quite general. These points may not be all global. They may be points defined over extension fields of the base field and things like this. On the other hand, they are clearly qualitatively different from the general object. It's such a drastic equation. By the way, the equation, of course, means that the isomorphism of the inclusion B into B to the A as constant maps. I should say that. The natural map relating B and B to the A should be invertible. That's the start of the Galois connection. So now, an attempt at representing C in the background B. Oh, and I say we're given A, so we generate the take the Galois closure of A. Those are the connected, whatever objects. Not that we start with the small A, the Galois connection is comparable to the category, even though it consists of very special objects. So an attempted representation is the background B, C in background B by figurative shape is defined by sending any object C to the co-reflection of C to the power A, where A runs to the subcategory A. In other words, we take the ordinary function space of the typical figure into the space in question, but then we take the co-discrete reflection of that, i.e. the points, or so to speak, the actual maps from A to C, considered as not in a discrete sense, some external sense, but in this internal sense, as being an object in this defined subcategory B. Now then we can extend the terminology of Isbell of adequacy, or if you prefer Elmholtz's range of density, by saying that A is adequate in C if this representation functor is full and faithful, again in this sense, by bijection of the semi-internal hump. Isbell's original formulation had the problem that depended on external set theory. But by internalizing relativizing to B, this relation between adequacy is first order, etc. So this assumption, namely the assumption that this little category is adequate for the whole thing, together with the precise description of A itself. This A consists precisely of circles and intervals, two-dimensional spheres, something like that for geometry, for Euclidean geometry. This would be appropriate. The precise description of A itself, together with the assumption that A is adequate in the whole, is a major step in axiomatizing both the theory of the category of categories and the geometrical categories of spatial nature and even of dynamical nature. So, again, I say for me that somehow this went from the category of categories to geometry, or wrote deep just started with. So implicitly, this is also a Rotary, although not explicitly recognized as internalized. Remember that the relationship between elementary toposes and Rotary toposes is really just a special case of Rotary's idea of relativization, because a morphism between two elementary toposes, with the second one satisfies strong axioms, being a universe of sets, is precisely Rotary's definition of utopos. See, actually Rotary never defined topos. They only defined utopos for a given base. Well, the base itself is a topos. So I outline some axioms for the categories based on a particular application of the idea of cohesive toposes that was originally developed for use in smooth algebraic geometry. So here we have negation and negation. Specifically, we will assume that the arrow, which is surely one of the objects in the desired A, is an amazingly tiny objectified motion. That is, that exponentiating by it emits a fractional exponent. We also touch upon the friendly nature of Leibnizian monads. So this extra right adjoint, of course, does not give categories its values. So what we're actually describing is sort of trapping the category of category in its usual guise between two different toposes. The smaller one will be these discrete objects. The larger one will be simply the recognition, well, basically set theory and category theory are quite consistent because categories are nothing but certain finite diagrams and sets, roughly speaking. So we can trap it between two toposes. Everything is topos. So in the larger topos, it will be an atom, and this implies all sorts of other stuff. For example, it must have the product with itself. A consequence of the existence of this extra right adjoint is a certain form of Robinson's principle about infinitesimals, except applied only for positive theories, namely x to the power I is a model of any kind of positive structure that x is a model of. Now, the maps between the powers of I are just the order-preserving maps between finite cubes. The first few of these are already adequate for the category of categories. 1, 2, 3, 4. But we need all finite products of it in order for the atom properties to mention the extra right adjoints. Now notice that the often mentioned simplicial shapes are retracts of the cubical shapes. The I-discrete, I being the interval, the arrow. The I-discrete objects are the discrete categories, intuitively, given the self-topos. And the reflection to them, taking the connected components of a general category, preserves finite products. The nullstellensatz holds in the sense that the discrete part of any object maps epimorphically to its discrete space of components. The truth value object of the big topos is connected because the interval has two distinct points. That's going to be cleaned up. Of course, the category itself doesn't contain this truth value object, but it's the truth value. Basically, the truth value object will classify all the sub-cubical things of any category, among which are the subcategories. So it classifies a bit more. Again, the logic of that in detail should be worked out. Now, so we use these of course are the figures. So the arrow is an I-shape. An I-shaped figure in A is just called morphism of A. If there's a one-shaped figure, it's called an object. And we can then deduce that a morphism in B to the A is a natural transformation. Why? because of the detailed structure of I times I. It's a community square. And, it's the ordered set I times I, four element partial ordered set. So. And in terms of this, the so-called common categories can be defined, as in my thesis, as pullbacks, and the notion of adjointness with its basic properties can be defined. The category C has a terminal object if and only if its terminal functor has a right adjoint. For each category with a terminal object, there is a canonical family of discrete categories, or in other words, an opt fibration parameterized by it, namely the fibers of the functor that goes from 1 comma C down to C. 1 comma C being the category whose objects are objects that C equipped with a point and community triangle. So the fibers of such a map are discrete, and so we have it's called an opt fibration. Such a family is full in categories, if any functor between any two fibers is induced by a map in C. Okay. So such a C represents a certain metacategory of discrete categories, if and only if every actual category in the metacategory is equivalent to one of the fibers of the family. Thus, the special object S that we want to single out should be one that represents, so in the sense of equivalence, all the small discrete categories. Having done so, having verified that S is a closed category so that other related categories can be independent, etc., we can carry out in a purely algebraic way all the established theories of general algebra, topos theory, their duality, linear algebra, functional analysis, blah, 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 as valued in S as a background. As valued in S as a background. So, I suppose the biggest sort of sets that arise in ordinary mathematics are Hilbert spaces and things like that. Well, they're well inside this whatever smallness is supposed to be. And that those structures involve taking small algebraic and spatial shapes, A, combinations. So this outlines the category of categories. So now the only thing is, what is this small? What is the metacategory small discrete that we're supposed to represent by this single actual object? So this particular smallness should be closed under exponentiation outside, so that the category S that represents would be Cartesian closed. So it has to be fairly big. Small should be fairly big, so it can incorporate mathematics. On the other hand, there's a very definite mathematical reason that S should not be too big, or more precisely, that it should not contain so-called measurable cardinals, or Ulam cardinals, or Anna-Tarski Ulam cardinals. The reason is well known for a long time, for that the duality between space and quantity, basic content of mathematics resides in this duality between space and quantity, is expressed in the fact, technically speaking, well known in the 50s, that any small metrizable space is real compact. And there are similar statements about uniform spaces, similar statements about morphological vector spaces, and they all involve some particular doctrine of the relation of space and quantity, and the intuition that this duality should be more or less perfect. And then there's a theorem, well, this duality is perfect if there are no measurable cardinals. So there's a whole series of results of that sort. So dialectically, we need to reject measurable cardinals. Well, the best way to do that is to embrace them completely by saying that there is an actual category that represents all the sets that are smaller than the first measurable cardinal, in which case that category itself will be comparable directly with the first measurable cardinal. So we will. Now let's notice that, again, I've been to many lectures on algebraic geometry, functional analysis, etc. When anybody comes to this theorem about if there are no measurable cardinals, and everybody says, well, they don't really know what measurable that scares them. See, the measurable variable is supposed to be a complicated idea, but it's extremely simple. In fact, it's an instance of the global principle of duality, for example, that Andres talks about in these lectures here, and so forth and so on. I take a simple formulation is this, that there is a small monoid M acting on a small set R, such that for all small sets X, the map from X into the M equivariant maps from R to the X into R is an isomorphism. Now, the maps from R, maybe I have some, yes. In other words, the M equivariant combing of R-valued measurements of X locates perfectly every point of X and excludes those points. So sort of Leibniz's principle with a vengeance. Now, Israel showed that, for example, taking M as all the endomorphisms of a countable set R gives a condition equivalent to those considered around 1930 by von Tarski and Ulam, who instead of the natural numbers used 2 as a dualizing object, but used infinitary operations on it, not just the unary ones, to test and define these putative or ghost points. So there are many actually formulations. So the one that the theory of the ring of continuous functions, which is closest to ordinary mathematical practice in some sense, is you take the real numbers as the dualizing object, and you just recognize it as a commutative ring. So the commutative ring homomorphisms from continuous real-valued functions on a space into real numbers itself includes those that are given by evaluation of the point of X, and the principle is that, well, every such evaluation should be given by an actual point of X. I think, to me, a further historically attractive alternative would be to say, well, this was already all figured out by the Greeks. In other words, if we take as a dualizing object the Euclidean plane, and we take the monoid of unary operations as those that are derived from conic sections in a certain way, we'll get the same theorem. So, but, you see, so now what I'm saying is, any notion of small should be, the actual category of representing small sets should have these properties. Nothing in it is measurable in this sense, and Cartesian close. But turning it around, we can define smallness to mean any X which satisfies this bijection will be called small. And then we can ask for an actual category which will represent it. So the desirable space quantity duality for the actual mathematical objects occurring in geometry, functional analysis, etc., requires only that it has not contained any non-small objects. Conversely, a very definite axiom is a requirement that all the small discrete categories in this sense can be represented by a single topos object S. This object itself, of course, is not small, even though it would be actual. About this passage between different dualizing objects, I should say that essentially these double dualization monads are arising by dualizing a given monad, where so the R that we start with, and hence all the R to the X's, are algebras, let's say over a certain monad, that has a limited arity. So it might be just binary operations or infinity array operations and so forth, but a fixed, again, an actual or false, whatever you want to call it, arity. And so there's a family. So you talk about, take some letters, you talk about a W tuple of T array operations, let's say. So for example, the notion of ring or distributed lattice and so forth involves essentially a pair of binary operations and a pair of null-array operations, subject to certain axioms, so that the arity is bounded. And the M sets I was talking about, of course, these are just unary operations. So there's a monad So the basic principle is that if you have a notion of algebras based on the W tuple of T area operations, you can replace it by another ground set. So you take any algebra X of that type, you can replace it by the function space X to the power of T, where T was the arity. And now on X to the T, there are just the unary operations parameterized by W to the power T. So W to the power T will typically include T to the T, which gives you sort of bookkeeping information so that you can recover the previous picture. But the crucial point is that this functor, which doesn't preserve underlying sets, is full and faithful. Now the category of all unary structures of that type, of course, is bigger, so there's more properties are required. This is sometimes called duality theory. So we find the properties which will enable you to squeeze back down from the unary operations back to the original thing. But for the purposes, you see, of testing whether double dualization reduces to the identity, which is the essential issue about eventual cardinals, you don't need to worry about the fact that the objects are more general, which is full and faithfulness, which is. Now, it's important to point out that there are many examples of this other than just. So for example, the original Lulan-Tarski formulation involving the set 2 as an infinitary algebra. So basically the operations are of what set theory is called the real numbers, i.e. maps from integers to integers, all of them parameterized unary operations. Sorry, the omega array operations. But now if you take 2 to the omega, that becomes a monad, which is that. Now Isbell, of course, remarked further, well, you can replace 2 to the omega by omega itself. So there's an additional step there. But essentially the fact that you turn it into unary operations is that. Well, there's a simple case of Isbell's structure, which is that the definition of ultrafilter can be described in terms of 3-area operations instead of 2-area operations. In other words, 3-valued logic, where all the propositional operations are unary, is just as good as Boolean algebras and all that, at least for straightening out the real elements from the ghost elements. Or if you like, for defining the monad whose algebras are arbitrary compact spaces, the beta, and so forth. But another example of this change of arity, so change of base algebra, which is fundamental in dynamics, is the passage from a second order differential equation living on a certain space to a first order equation operating on the tangent space. So just to a vector field, the unary operation acting on the tangent space, because we realized, and we weren't the first to do so, already Gabriel and and so forth, realized this, so that the so-called Lawvere axiom was in some form known already before. But the basic point is that the tangent bundle is a special case of the Hurwitz exponentiation, just that the exponent is a certain infinitesimal space called D. Well, the second order equation is a family of D-area operations parameterized by a second order infinitesimal space. So if you pass to the tangent bundle, well, that's an exponential space, as I said, and on that operates the space of all maps from first order infinitesimal to second order infinitesimal, which can be, realized as certain polynomials of low degree satisfying certain vanishing conditions on the coefficients, and so forth. But it becomes, this exponential of infinitesimal spaces becomes a macroscopic space by a fundamental observation of Euler. But at any rate, this vector field associated, a vector field on the tangent plane associated to the second order equation on any given configuration space, together with the homogeneity necessary to recover the original space from it, is a special case of this same transformation that I described in general terms. W to the power t tuple to unary operations derived from a W tuple or t array operation, but on the space x to the t. How are we spending the time?
You're speaking for just over an hour.
So plenty of time to read the second page.
No, come on.
I know that's why I made it do it. No, as I say, you've got another 20 minutes or so.
Oh, really?
Yeah,
Oh, okay.
We've got another 20, 25 minutes, and then we have that discussion.
Oh, okay, great. So maybe I can, yes, can go back and outline what Frege really meant.
Sorry, do you mind if a few questions?
Go ahead, finish. Yeah.
So not being a logician and anything, I didn't understand that. It seems you might be
Are you
after,
accusing me of being a logician?
you might be after
Careful.
something like tame logic. And my question was, how does this tie up, if it does at all, with what you were saying about selecting certain homomorphisms of the interval in order to define and tame logic in an intrinsic way?
Yeah.
Yeah, does it at all tie up with that?
Well, I mean, it certainly ties up with this general
Yeah.
ideology of figures and situations.
Yeah, that's what I mean, but there's even more technical way. in which-
In other words, could we relate the attempt to find that sort of truthos directly with the categories, for example?
For instance.
Well, that's what Grothendieck does
Yeah.
in his long description of how to extract homotopy theory, for example. Any species category. There's a direct relation.
Mhm.
It's a bit strange, it's a very strange thing that is homotopy theory away, because he replaces, as I did here, the presheet by its corresponding fiber category with discrete fibers over the original base, but then he takes the total category and throws away the base. So the thing that you constructed had a meaning in terms of the family, and so you throw away the base, which sort of corresponds to the idea that in doing homotopy, you just have to get from here to there. You don't care what label, what cost of the ticket it is to get from there. So the underlying vibration somehow records, well, it's a label for the kind of area that you used, and you throw that away, you still have the existence of these areas, and that's all that's required for
You mean on the standard equivalent, where
well, you
you
get
exomatise
you get
what
equivalent-
vibrations are
you get equivalent model structure.
Yeah,
Consistent.
you get equivalent model
But this is a more concrete construction, it's a specific construction. Yeah, so, again, the other way, I start off in a similar way, namely, the subsets that are useful in advanced calculus, and students are sort of seduced into thinking that these are subsets of some kind of universe and so forth. Specified by properties, so that all concepts of properties, et cetera, was the Frege. Now, the specification of subsets of a given universe often proceeds in terms of properties that elements might have. I mean, you might single it out in another way, but very typically the properties of the elements. And this led, in fact, the idealist philosopher Frege to the speculation that all concepts are properties, abandoning the logical principle that properties are defined on a definite universe of discourse. His properties could only be defined on everything. But actually the meaning of properties is only relative to a structure that the universe of discourse carries. Thus, beyond generalities about inclusions, Frege's, quote, everything required some kind of structure, so he was very pleased when Peano made explicit the following. He wrote him a letter saying he was pleased. Among all the sets, so now these are just subsets of the grand universe, like metasets. There are the minimal ones, or the atomic ones. I mean, obviously the subsets of the universe have inclusion relations, implications for these properties and so forth. So that we will have. So there are the minimal ones. A, having the property that if B is included in A, then B equals 0 or B equals A. And there are variations on this definition. The idea of the minimal one is not 0, and yet there's nothing in between it and 0. Now, then there's a property that you could assume about the whole universe, obviously motivated, in my case, directly from Isabel's idea of adequacy for categories, but in this case applying to cosets, namely that in order to test whether set X is included in a set Y, it suffices to show that for every atom A, for every minimal A, if A is contained in X, then it's contained in Y. So the universal implication among inclusions now, but restricted to these minimal objects. So this somehow is the basic setup. You could call it extensionality of a coset, or I guess I will always assume it's semi-lattice. But this extensionality does not involve either singleton nor epsilon, but just this concept of minimal. But now there's a further thing, and this is somehow Peano's contribution, and I'm striving to make it as ridiculous as I can, so don't. It means that every set has been somehow assigned an address, which is such an atom, and this is denoted by singleton X. Just arbitrary, just a label. So we're talking about, computers are all full of labels or something. So each actual set, or at least every small one, let's say every set, has been assigned a name, and it is such an atom. So in terms of this, the other contribution, the epsilon, is defined by saying X is a member of A, means that the label of X is included in A. So this is how, and I think Peano himself describes it in that way. I know that one prominent set theorist, at least named Jensen, explicitly formulates his framework first in terms of inclusions, and then with this extra structure, which is some sense of generalized structure on the universe now, where the inclusion was just part of the logic of property, the special property. Now, Cantor actually protested vehemently against all this. Again, there's fragments of Cantor's writings that are actually included into his collected works, so select works, even though the editor didn't like them. And Zermelo, namely that editor in 1930, sided with Frege against Cantor. Von Neumann followed Zermelo, leading to the cumulative hierarchy and parting with the rest of mathematics. The prestige of von Neumann, for various reasons, together with Gödel's application of it, led to the acceptance of that hierarchy as, so to speak, the default determination of the term set theory and of the term set. Completely different from the mathematical one. It has been developed into a powerful tool for proving statements about itself, and also a powerful tool for prolonging the idealist speculations of Cantor's later years concerning an endless climb toward absolute infinity. Somehow this idea of absolute infinity is worth a lot of money these days, as has been pointed out. So I'm taking way, this is, I'm not a professional biographer. I think that's sometimes considered a cheap trick to distinguish between the young angles and the old angles and so forth. But it seems to be there in Cantor's. Now, so what I'm saying is that one can develop this conception about the up semi-lattice of sets to it further, in particular by saying, again, from the point of view of category theory, or mathematics, that even though, independently from this atom business, this extension atom business, it makes sense to speak about adjoints and posets. And so there's two fundamental adjoints, namely union and power set. And actually, union of A is included in B, if and only if A is included in power set. So to all of us, that should instantly say, aha, these are adjoints. So we postulate that these two further operations, which are adjoint, and of course, in the parser order case, there's a tendency for adjoints to be idempotent. So this actually describes a sub system which corresponds to what's usually called transitive sets. So the transitive sets are an important tool in set theory. Now, the very fact that power set is the right adjoint tells you that it preserves the terminal object, if there is one. On the other hand, Cantor was pretty sure that the power set was always bigger. You see. Conclusion, there is no top element of this poset. In other words, these kind of semi-philosophical arguments are precise algebra. So one can continue in this vein and try to figure out if there is any rational meaning to this assignment of the so-called singleton.
The Frege-Piano picture, if I understood, the Frege-Piano picture is, as it were, fixing, somehow metaphysically fixing a globally fixed element.
No, not an element. The universe of discourse is fixed, and then there are many subsets of it, and which represent elements which represent subsets, but the top element cannot be represented by.
No, I meant in terms of the last inclusion of parts of the universe of discourse.
Yeah, there is no greatest element in terms of this inclusion.
Yeah.
If you want P to be non
Yeah, exactly.
because otherwise. So a good deal of the constructions in set theory actually can be phrased in terms of this extra structure of the two adjoint operations, union and power set. And so I keep this in mind when I try to struggle through the texts on set theory in order to try to, you see, so to figure out these two basic problems. I've touched on their definition of small. I think the theory of that, this particular kind of double dualization and so forth, should be considered as something very elementary. It could be described as just as obvious as actually as the first part of it and so on. But the other thing, we're coming back to it, is what is this idea really, really abstract, really, really constant, really, really not properties. And it's in such a way that the continuum hypothesis would follow from it, but that it's somehow more basic, that it really really expresses directly this idea of constancy. And I should mention, what I think, this is just a suggestion, something to understand here, namely, the strategy is we have to reject as a final answer this idea of Gödel's L, because iteration really has, this imaginary iteration, really has nothing to do with it. And on the other hand, we do want to include a representative for all small sets, in other words, equivalent that measurable cardinal. And there's a well-known result of Dana Scott, which says measurable cardinals are incompatible with constructibility, at least. However, there's from this point of view, there's an important model constructed by Silver, which says that it constructs a model which has two properties. It has one measurable cardinal, as we are asking for, and on the other hand, it satisfies the GCH, not B equals L, but the most famous consequence of that, which is GCH. So that somehow the direct elementary construction of this Silver model would be the kind of thing that would help to clarify. And another general word about that is, well, you see, in topos theory, we really have a well-developed idea of more or less cohesion, more or less variation, as given by geometric morphism of topos. However, now, you can't say that B is enriched in L, because I would say the Hom set of two sets is constructible. It's not true. So basically, the correct theory of what's more variable, what's more cohesive, what's more or less to minimalize, should involve functorial comparisons between categories, which only go in one direction, which don't have adjoints, after all. And again, there's a big fragment of that in Gödel's notion of absolute property. So to the study of left exact functors between two toposes which don't have adjoints, and there's a whole chapter for other purposes of that, but another chapter of that should enable us to make more precise this idea of greater or lesser discreteness, and hence hypothesize some extreme form of discreteness. For the sole purpose of providing, it's not that this absolute discreteness is somehow a desirable goal, it's just to clarify by passing to the extreme this nature of fundamental struggle between continuous and discrete.
Very much indeed, Will. Okay, well, we have about 15-20 minutes for questions, and then we'll take a short break before Colin speaks.
I wonder, have you looked into the possibility? I don't see offhand why you couldn't have a model of Zimmermann-Lefranco with a measurable cardinal, where V does equal L below that measurable cardinal.
Yeah, below that's an obvious conjecture, and I don't know if that has been considered. Yeah, that seems to me the first thing to ask after you hear Scott's results.
Yeah.
But I've never seen it addressed as such. Because Silver instead gets this weaker assumption that GCH holds all the way.
Yeah, because the intermodal approach to measurable cardinals, the measurable cardinal's first critical point is the first thing that's moved by the intermodal. That is to say, everything below it is unmoved. Yeah. And that doesn't mean that it could all be constructible, but it sort of looks even more
it could, maybe.
Why couldn't it all be good?
Yeah.
It's all unmoved by this.
Yeah, I mean, obviously, to pursue my program, one has to study what people have done with constructible sets, even if you want in the end to reject that whole idea. But so much information about it has been so cheap.
But it certainly has the flavour of, enforcing constancy as far as, it can be enforced below that. Below that.
Well, yeah, I think it's enforcing constancy sort of more than we need.
Yeah, no, sure. I don't
Well, we need a lot,
but the particular example, as I say, which Colin was discussing.
but in spite of my posing this problem, you see, I hope people don't take seriously the Wikipedia article which claims that Gödel toposes are about geometry and the real toposes are about logic. Well, certainly the elementary toposes arose from geometric considerations with the realization, well, a certain side comment involving some explicit use of logic is needed.
Yeah, and it's just bizarre to say the difference between geometry and logic is that geometry requires set power of completeness.
Yes, that's right. Good point, yeah.
Could be.
Excuse me, I have before that I have
Yeah.
one question, a couple of comments. My first question is, somewhere toward the end of that book, Conceptual Mathematics, you draw a figure, which is F, and then you have G, and then there's H, and connecting that F and G, right? G composed with H is F.
Yes.
Is that somehow related to the objective logic you mentioned earlier?
Well, that's showing how subjective logic is incorporated into it.
Subjective logic.
Subjective logic is incorporated into objective.
And,
I mean, if you're not familiar, this is Grothendieck's definition in a Tohoku journal, 1957, showing that both inclusion of subsets and membership of figures in subsets can be expressed by exactly the same thing. Right? So that this, in other words, the commutative triangle, typically we write a dotted arrow for the H, meaning that its mere existence is enough to prove that the first one is fully included in the second. And normally there are two special restrictions on that. If we assume that both of these arrows are monomorphisms, i.e. precisely according to Grothendieck subobjects, then this is a proof that one subobject is included into the other. And the other special case is where one of these things is a subset, but the other one is an arbitrary figure, but perhaps of a specified shape that we happen to like. So we said these specified figures might belong to a subset. That's again exactly the same diagram, except that the figures are not necessarily non-singular. They might be singular, they're not required to be equivalent to subsets. So that's precisely. So another, in turn, then, you see what the subjective logic of statements or properties implying others, etc., really describes subobjects of some universe. And so in that sense, we are interpreting subjective logic into the other.
yeah, I think I have to re-listen again and again by that exposition. And then the second part is the verbal comments. You mentioned von Neumann.
Yeah.
Then for him, somewhere in his paper written in the 1920s, he says something like this. For meta language or meta logic, he takes intuitionistic logic. And for objective logic, he takes classical logic. Another similar sort of thought is expressed as to his choice of a function as when he gave the formalization of the axiomatic system.
Yeah.
And in his, my memory is not precise, but something like this. In mathematics, the main central notion is function, and not in the logical or philosophical sense, but from the working mathematician's point of view.
Yeah.
And then, therefore, he takes a certain function, whichever you take, not so much different, but he says in functions, he didn't say popular, but it's a major object of present-day mathematics, so he takes. The last comment is,
Of course, he then takes this everyday idea and applies it to the universe. So his functions are always functions from the universe to itself. So it's a little bit different from those of calculus, actually. Sorry.
Okay. And the last comment is you mentioned Cermello and Cantor, but then Cermello wrote a paper just after 1931 or so, and then he introduced, well, the title of that paper is Grenzzahlen, that means strongly inaccessible cardinal. And if I'm not wrong, he said something like this. Take the universe, which is at the top of that level, is the strongly inaccessible cardinal. And that sort of von Neumann universe chopped at that level, he regards it as a sort of a representation of Cantor absolute. and he refers to, within parentheses, he refers to some constructive intuition in German term, and that's probably from Kantian epistemology, but I'm not certain. From Kantian epistemology.
Ah.
But, and then, yeah, sorry, that's not the final. The final one is, you mentioned the collected work of Cantor, edited by Cernello, and there's an article written by Cantor referring to Frege.
Yes.
And then editorial commented, these two big mathematicians could not understand each other. But he wrote, Cernello as an editor, he wrote just some comment on that sort of comment. But I don't think, well, if you look at the Frege's and Cantor's original correspondence, these two figures really understood each other as to the differences between their fundamental notions. But that's
Yeah.
Thank you. Thank you very much for the comments and the question.
Oh, very good. You can tell.
and I'll let you know the development.
Thank you. Okay, do we have some further comments and questions? Bernardis or Anders? Fine, anybody? Well, in that case, do you want to? Okay, well, there was one question I wanted to put, which is I'd like to get a little clearer on this relationship between the inclusion theoretic, or lattice theoretic nature of the structure of the universal discourse, obviously given the indispensability of the universal discourse principle, and what it is that the Frege-Piano singleton notion is doing, as it were, to distort that picture by rigidifying this notion of global and absolute membership.
Yeah.
I mean, how you see the lattice theoretical relationship of parts of the domain as being affected by that. It seems that there's some notion of some metaphysical minimality of the smallest. Okay, sorry, I'm not expressing this very clearly. But yeah, can you say just a little bit more about the relationship between
What I'm saying was
inclusion and
this assignment. So if you imagine this huge partial set, which has finite unions, basically,
Yeah.
it's no top element.
Yeah, that's the point.
And these two adjoint operators, which give it a relatively rich structure, which you can use to express many ideas of the hierarchy. But then this singleton business, you see, what I'm trying to emphasize is that by this act of unifying is artificial. That this is an arbitrary address, you see, in the same way that your phone number is arbitrary. It just keeps track of you as a living set, as a mere dot somewhere else. You just have enough of them, you see. So the project is to show that models of this theory, this algebra that I just outlined, you see, permit actually a large number of choices of this thing. Another way to look at this arbitrariness is, okay, we're going to iterate the power set. Well, the power set we know is a monad, and we know that from any monad we get a simplicial structure. So along which of these maps are we going to unify? Are we going to take the union? We could imagine taking the direct limit of these transitions, but which is the preferred? We are sort of throwing away this simplicial structure of the iterated power set by just taking a flat union, which is again. So, I mean, this is kind of a propaganda exercise in a certain way, just but by clarifying the algebra of the thing to illustrate how really arbitrary this is. Poor children are, innocents are led to believe that we can take union of A and the power set of A somewhere without specifying, where the where is.
Yeah.
We want to try to close that by algebra.
Yes. And then also to think that one can arbitrarily iterate the power set formation in turn.
I wanted to make another remark about the power set, by the way. see, this business about the excluding the ghost elements and so on from the double dual. It's one attitude is Isabel did, is that when you take all operations, and if they can't succeed, that means that the real numbers are small. So sort of this implicit row-bottom result there that our into the end isn't enough to strain out the truth from all these observations that are there. But actually, one thinks of this power set, for example, it has a multiplicative and an additive part, and additive categories have all sorts of advantages that we learned since the early 50s. Okay? So the point is that the power, not only is singleton, or the Dirac delta type map, the unit of the monad is there, but that there's a natural map of monads from the full power set into this double dual. This double dual, from that point of view, is kind of a, and you take just union preserving maps in the double dual, maybe arbitrary unions, which will splash you back down to power set, or countable unions, which is the crucial one. So it's a larger power set, not a smaller one, as some other people advocate. It's something larger than the actual power set, which in other ways is very much like the power set. So in some sense, there is this point. Well, instead of demanding that there are no ghost elements by using addition and multiplication, let's just use addition and say, well, X is small enough if the countable union preserving functionals are representable by sets, by subsets rather than elements. And it's easy, it's an elementary calculation to show that if you have one of these functionals represented by a set, that set reduces to a point if and only if it preserves finite unions. Preserves multiplication, which in statistics is known as standard deviation 0. So this is a suggested approach using slightly more concrete mathematical operations than just arbitrary operations to approach the same goal of understanding these related double dualizations.
Right. And the other thing I was wondering if you would be ready to say just a little bit more about before we close is how something which you touched on towards the beginning of the talk, which is the way in which one should see the axiom of choice as enforcing the condition of absence of cohesion. In the case of, and particularly obviously the cohesive cohesion and variations, particularly involve negation of choice, but precisely because choice involves the existence of a local section functor. Whereas cohesion, as one sees in the case of chronology, typically deals with the conditions of the existence of obstructions to inverses of maps, and hence to the absence of global section functor. I was just wondering if you could say a little bit more about how that fits within the picture.
Objects have a non-trivial combinatorial form, usually can be traced to the failure of the existence of sections somewhere or others, so that by contrast the denial of cohesion or form that might be resulting from traces of motion or all that is for practical purposes, i.e. for everyday mathematics, the axiom of choice is sufficient to exclude cohesion and variation. It's only rarely that we come across, the continuum hypothesis, for example, which is a stronger statement in my analysis, and a stronger statement in the same direction. Then, of course, we know that even that is independent of the known axioms, so to speak. So that axiom of choice is only the first approximation, but it's a very good approximation for practical purposes.
Well, thank you very much. It's very limiting. Again, I very much regret that Lawvere is not here because he has written on this subject, particularly on the geometric and topological corollaries of both choice and extensionality principles in the topos setting. As well. And it's devoted quite a lot of time to thinking about those issues in connection also with the cognitive dimension. foundational notions, which Jean-Pierre was speaking a little bit about yesterday morning. And we would have been very nice to have got his reaction to this wonderful talk. But as I said, we'll be able to send him the video and get his comments, and then those are some of our other friends who are not here. Are there any further questions or comments? Pierre or Colin? Okay, well in that case, can we thank Bill again for settling down? By the way, as Bill just mentioned in passing, tomorrow afternoon, we only have two talks.